Hi, this is Prithvi. Today I'm going to explain you about the final project in recurrent neural networks for sequence data. Firstly, I'm going to explain you about the seminar which was held on our last class, which is about journey of generative AI from Boltzmann distribution and Markov chain to large language model. The evolution of generative AI, contributions of RNN and LSTM variations, the creation of new content or data that emulates human creativity is known as generative AI, and it has advanced significantly in recent years, primarily because of development in recurrent neural networks and their variants, such as long short term memory networks. These neural network topologies have transformed the way computers comprehend and produce sequential data, which has resulted in important advances in a variety of creative tasks, including the creation of images, music, and natural language. The capacity of RNNs and LSTM networks to model and capture temporal connections within sequential data is one of their primary contributions to generative AI. Because they don't have memory, traditional feed-forward neural networks aren't appropriate for jobs where context and order are important, such as language modeling or sequence prediction. To overcome this constraint, RNN incorporate loops into the network architecture, which let data remain persistent over time and let the model handle sequences of any length. The development of LSTM networks, a specialized version of RNN, expanded generative AI's potential. Standard RNN have a problem with gradients diminishing as they propagate back in time, which makes it difficult to learn long-range relationships. LSTM solve this problem to improve their ability to capture long-term dependencies in sequential data. LSTM can be made to selectively retain or forget information over time by integrating gated units that control the flow of information. This discovery has significantly changed a range of generative tasks by allowing models to provide output that are coherent and rich in context. In particular, long short-term memory networks and other variants of recurrent neural networks have been essential to the development of generative artificial intelligence. These architectures have completely changed how computers generate and analyze sequential data, opening the door for incredible advances in text production, speech recognition, and natural language processing, among other fields. Neural networks that are specifically engineered to process sequential data, including speech, text, or time series data, are called RNN. RNN contain an internal state that enables them to keep a memory of previous inputs and utilize this knowledge to generate predictions about the current input, in contrast to typical feed-forward neural networks, which function on fixed size input and output vectors. RNN are especially well suited for tasks involving sequential data such as language modeling, machine translation, and speech recognition because of their capacity to acquire and use context. The vanishing gradient problem, which affects conventional RNN, makes it challenging for the network to identify long-range dependencies in the input. The introduction of LSTM network, a put out by kind of RNN put out by Hochreiter and Huber in 1997, overcame this drawback. Long-term dependencies can be more accurately captured by LSTM networks thanks to their more advanced gating mechanism, which enables them to selectively remember and forget information from previous inputs. The development of generative AI models has benefited greatly from introducing LSTM networks and their capacity to manage long-range dependencies in sequential data. Text generation and language modeling were one of the first and most important uses of LSTM networks in generative AI. Researchers were able to develop models that could produce text that resembled that of a human being by translating LSTM networks on sizable text corpora. This created new opportunities for applications including machine translation, dialogue systems, and creative writing. The creation of generative adversarial networks, a potent para- paradigm for generative AI, was also greatly aided by LSTM networks. Two neural networks, a discriminator and a generator, that have been trained in competition make up a GAN. While the while the discriminator network attempts to dis, discern between produced and real data, the generator network learns to produce synthetic data, such as text or images, that mimics the real data. For applications including text, music, and video synthesis, LSTM networks have been employed in the generator com- component of generative adversarial networks, allowing the creation of synthetic data that is more realistic and cohesive. In conclusion, it is important to exaggerate the roles that RNN and LSTM variants have played in the development of generative AI. Neural networks topologies have revolutionized the understanding, modeling, and generation of sequential data by machines, resulting in advancements in a wide range of creative fields. Leveraging these developments ethically and responsibly will be essential to realizing the full promise of generative AI research for the good of society as it moves forward. Part 2, a time series dataset. The specifications of this dataset are name of the dataset is vehicles with the lowest and highest real world fuel economy by model per year source, US Environmental Protection Agency, and the website is investigate automotive trends data, and the download link is download dataset, and the file format of this is CSV file format, which is used for this data. Dataset details are time series span from 1975 until 2022, which is 47 years. Number of data points, the total number of data points is 243, and the number of variables is 16, and the data types are rank, new, numeric, regulatory class, categorical, model year numeric, manufacturer categorical, model name categorical, and vehicle type is also categorical, weight is numeric, derived drive type categorical, transmission categorical, gears numeric, fuel delivery categorical, horsepower numeric, engine displacement, and real world MPG city, real world MPG highway, real world MPG are all numeric. This data can be used to compare various automobile models, look at trends in fuel efficiency, and learn more about the energy and environmental impacts of automotive sector. Real world fuel efficiency is fully understood when aspects like gasoline distribution, driving type, weight, and regulatory class are considered. Part 3, RNN, simple RNN with sine wave data. This diagram represents the architecture of neural network. which consists of 70 neurons, which also includes four neurons which are in the input layer, and 65 neurons which are hidden layer 1, and the output layer contains one neuron. This project's main goal was to develop a time series forecasting model that could predict sine wave values using TensorFlow and recurrent neural networks. The implementation made use of NumPy, Pandas, Matplotlib, TensorFlow, the time series generator in TensorFlow, and the minimum maximum scalar in scikit-learn. Data generation. Using NumPy's line space function, a sine wave was first produced. The generated sine wave was visually assessed using a visualization, and the data was then placed into a pandas frame. Data splitting. Thir- 30% of the data was put aside for testing, while the remaining 70% was set aside for training. Data normalization using minimum maximum scalar for scikit-learn. The data was normalized after being trained on training data. The scalar was used on testing and training datasets. Time series generator instance. Using Keras time series generator function, a time series generator was made to make training and testing the model easier. With 40 historical data points used to estimate the next outcome, this generator was configured to generate batches of time series data. Model construction, training, and testing. A simple RNN model including a single simple RNN layer with 70 neurons and a fully connected layer for the final prediction was constructed using Keras. Model evaluation on test data. By making predictions repeatedly, test data was used to evaluate the model's effectiveness. The model's prediction and the actual outcomes were compared by the low MSE score of 0.0058, which suggested that it could produce precise prediction based on historical data. Training epochs. A training process snippet with illustrations showing the loss reduction from the first epoch was given. All things considered, this work demonstrations how RNN may be used to predict time series more, especially sine wave values. The model's accuracy is highlighted by the graphic comparison between the anticipated sine wave and the original data. RNN Part 4. LSTM Neural Networks. Explain the vanishing and gradient problem. An ongoing difficulty in neural network training, especially in deep architectures, is the vanishing gradient problem. The phenomenon occurs when the cost function's gradients almost approach zero, but about the weight in the network's initial layer. This makes it more difficult for these layers to update their weights effectively, which significantly reduces the network's ability to make accurate prediction. The main reason for this problem is that during backpropagation, gradients multiply again as they go backward through the layers. With every layer, the gradients get smaller and smaller until they finally vanish completely in the early going. Gradient disappearance causes important information to be lost and restricts the network's capacity to learn meaningful representations of the input data. The size of gradients at each layer backpropagation is highlighted in the diagram below, which shows a deep neural network with many layers. Darker colors indicate larger gradients. Interestingly, gradients amplitudes rapidly fall in the early layers, leading to slow weight updates at those levels. This is the diagram of the backpropagation. Choosing the right activation function and network architecture is essential to solving the vanishing gradient problem. Rectified layer unit and other activation functions that preserve constant gradient magnitudes are suggested as a solution to lessen the issue.